I'm going to give a quick overview of radiation patterns from oscillating dipoles manifested in conductors as changing currents in time, and in insulators as changing polarization in time. And in insulators, Fermi's golden rule applies, but I'll talk about that in a separate video. Also, I'll be using phasors because it's easier to do math in the Fourier space using frequency components. I'll start off by discussing just general relationships between sources, potentials, and fields, then discuss the specifics of the radiation patterns. Here I've written out the electric field and the magnetic field, and I've combined them into the Helmholtz equation for the vector potential. And I've invoked the Lorentz gauge to eliminate this term. This is all just standard E&M algebra. So now the E field and the H field are both simple functions of just the vector potential. And we can simplify the problem by only considering z-directed currents. I can solve this problem in at least 3 different ways, and if it were more complicated, I would go about finding a green function solution for the vector potential A when the source is a delta function. But I don't want to go through the whole process of finding a green function in this video. That'll be another video. So I'll just use a delta function here for the source and pretend like I'm solving it using a green function and just guess a function for the vector potential. And guessing a solution is standard practice in differential equations, so I don't feel too bad about that. So now we look at the Helmholtz equation as a green function equation. That we're using a point source, so we use delta functions representing in 3 space, even though we're talking about just the z-directed component now. The driving function represented by the delta functions, even though it's z-directed, still is localized in 3 dimensions. So then we know that the green function must be only dependent on r and not on theta or phi, the directions. But that does not imply that the vector potential is also only a function of r. And as we'll see shortly, it is not. Now, knowing that the green function is only a function of r, I expand the Laplacian and guess a solution for G. The solution should describe a wave traveling away from the source, so C2 must be 0. Now, to get this solution, I set the source equal to 0, so we're obviously not at the point where the source is located. We're everywhere else to get this solution. And as we approach the source, it's a simple limiting procedure to show that the solution is still valid. The next step I'm going to make is also somewhat hand-wavy, but still valid, considering the static case where beta is now 0, and omega is 0, so beta is 0. So then the Helmholtz equation is reduced to a Poisson's equation, and the solution is just C1 over R. Of course, now we're considering the full scope of the source, so then the solution is the vector potential rather than just the green function. The green function is just a method for finding a solution that is valid once we expand the problem to more than just a point source. Now we can take this general solution and find the full solution for the static case and use this as a model to extend to the dynamic case. noting that the only difference is that we have this extra exponential term. So we can use this to write out the full solution for the dynamic case. Don't get confused by the fact that we have this green function here by itself and all the rest are the actual vector potential. We use the green function as a solution to the more complex Helmholtz equation for the dynamic system. And for the static system, it wasn't necessary to find the green function, so we just used the vector potential itself. Also note that these exponential plane waves are just manifestations of the retarded potential. So if we're looking at these problems, or these solutions rather, as full time-dependent solutions rather than phasors, we would see that these were just delayed signals due to the retarded potential. But since we're looking at the phasor, we don't actually consider the time component. It's another way of saying that we're looking at the frequency, the Fourier components. So now we have the vector potential. We can use that to find the field patterns, and we'll need to define a current distribution, which will start off with a Hertzian dipole, which is an infinitesimal oscillation, and we'll use the z direction. So because it's infinitesimal, big R is equal to little r to 0th order. This is an approximation, but it's exact to 0th order. So now we're left with the vector potential as this very simple function. This vector potential formulation was derived following 3 antenna engineering books and cross-checking against optics books, as well as pure physics theory books. And the antenna engineering books particularly were useful: Balanis, Stutzman, and Krauss. And when cross-checking against such as Griffith's E&M, these vector potentials are essentially identical once I make some simple modifications to Griffith's formulation. I'm only showing the outcome of Griffith's derivation for the vector potential that he does in the time domain, and he starts with the retarded scalar potential, so it's quite different. But you can see the equivalence between the two derivations, and we get the consequence of the retarded potential for free by using phasors. And we'll also continue on much further into the radiation patterns than any of the theory books that I've gone over have done. Let's move on now to develop this scheme for visualizing the radiation patterns. We have the vector potential here, and it's straightforward to find the H field from the curl of A. And then instead of using the previous equation for the electric field, I'll use this curl of H, which is straightforward, though not necessarily simple to do the math. I'm just going to write it. I need more room. Now I've said that this is the development for the ideal dipole radiation patterns, but said nothing about the distances from the source. So what we want to do is analyze the far fields. That's where we typically consider radiation, though there's also what's called the near field radiation, the Fresnel region, which we'll talk about in a minute. But these are the electric and magnetic fields when we consider distances far away from the source. Now let's look at why these are called radiation fields. The power or power density given by the pointing vector must be real. It must be radially directed, and the total power radiated must be independent of distance r, so that all the power is radiated to infinity, which means the power is decoupled from the source and from the near fields. This defines a radiation field as compared to, or as opposed to, a reactive field that stores energy and it doesn't radiate it to infinity. Now let's look at the non-ideal case for electrically small dipoles. We'll take a current oscillating in the z direction for simplicity again, and we're still using the same development with the green function method used to solve Helmholtz equation up to this point. This time we use the parallel array approximation for R due to the finite extent of the dipole in the z direction. This is a first order approximation. If we wanted to find the near field radiation in the Fresnel region, then we would use a second order approximation. For this first order approximation, going through the same steps as we did before, now we have the E and H field. The integrals in these field expressions that include the current distributions are called a space factor. For a continuous distribution, it's called an array factor. For a discrete distribution, so in this case it's called a space factor. Now we have the field expressions for both the ideal dipole and the non-ideal small dipole, and we'll focus on the electric field from here on out. And it's easier to compare what's called normalized field pattern expression, where we take the fields and we normalize them to their maximum and normalize out the radial component. Now we have the normalized field patterns for both cases, the ideal and the non-ideal small dipole. And for the ideal case, this solution is always called an element factor. And from the beginning, we started with a particular type of current distribution that we used an infinitesimal source to find the solution for the Green's function. And the element factor is dependent on the type of current that we choose in that case and the direction. And we chose a z direction, so we get a sine theta. If we had chosen orthogonal to the z direction, we would get a cosine theta. Or if we had chosen a different type of current, for example, an aperture current, then we would get something different than sine theta or cosine theta. And that element factor always comes into play with the non-ideal case in what's called pattern multiplication, where you get the element factor multiplying the space factor. So if we rewrite this without the R dependence has gone away, then you can see that we have the element factor multiplying the space factor. And for the discrete case, with discrete current sources placed in an array, it's called an array factor. So here we have the radiation pattern for the ideal dipole in the far field region, the Fraunhofer region. And it's only showing the angular dependence. So this pattern multiplies the space factor to get the full pattern factor. This ideal pattern has azimuthal symmetry, though I've only shown two planes in the three-dimensional drawing. Now for the non-ideal pattern, we'll use a constant current at first to develop a more advanced visualization technique that simplifies the analysis. Now after integrating and analyzing the denominator for the theta, which gives it a max, we have this pattern factor with the element factor and the space factor. Now if we take the space factor and do a simple u substitution, then this function of u, that's a sinc function in this case, is called the universal pattern factor. And if we plot the magnitude of it and extract that down to the function of theta plot, then it makes it easier to visualize the real space theta pattern as compared to the u space universal pattern factor. And I'll explain this beta naught and theta naught next as they come into play for more general current distributions than what we've given this one as a constant distribution. In order to illustrate the mapping from the U space pattern to the theta space pattern, I'll introduce this uniform current with non-zero phase, which can be thought of as having a free space plane wave with propagation constant beta incident on an oscillating dipole at an angle that results in the propagation constant of the oscillator beta naught that could be or could not be equal to beta. So then the unnormalized space factor written in the universal pattern variable u takes on this current phase factor in the variable u. Now when we plot the universal pattern and transform to the polar plot, we can see how the beta free space propagation constant affects the plot, and compare with how beta naught, the dipole propagation constant or material propagation constant, affects the plot. And note that beta, the free space propagation constant, determines the radius of the half circle, while beta naught determines the initial angle of the main lobe of the pattern and the offset of the half circle. Now let's take one last look at the continuous pattern and the unnormalized space factor. I've included here a general current distribution amplitude, and the phase factor for the current is still buried in the variable u. Now if I take this and extend the limits of the integration to infinity and minus infinity, then this is just an inverse Fourier transform. So then we have this relationship between the current amplitude and the space factor. So if we know the pattern that we want, then we can synthesize the current by this process called beam shaping. Now by discretizing our continuous source distribution, not only can we find antenna patterns for discrete distribution of sources, we can also use this same derivation for crystallography to determine crystal structure, and leading to an understanding of energy dispersion relations in materials. We can also use it to determine radiation absorption due to nucleated sites and photoconductive materials. So now if we analyze this discrete array, we can use the space factor from before that was a continuous function and discretize it so that we have the array factor here, where alpha is the delay between the n plus 1th to the nth element. So the n plus 1th element leads the nth element by alpha. And we're going to want to do the same pattern transformation as before, so we'll replace this with an expression with the variable psi. And finally, here's the construction technique for finding the array factor as a function of the polar angle theta, or vice versa for the discrete case. And note that the number of nodes within a 2 pi period for the variable psi is equal to the number of array elements minus 1, and not all of those nodes will be within the visible region in the polar plot. And that concludes this video for radiation patterns.